Throughout human history, we've built an incredible body of knowledge about the universe around us. However, we're only at the beginning of this journey. The universe is a twilight zone of secrets, unexplained mysteries, and black holes shaped by unseen forces. In this video, we will reveal some of them. What lies beyond the universe? Does Planet 9 really exist? Is there life on Jupiter's moon? What did Voyagers 1 and 2 detect beyond our solar system? It is generally considered that the universe has no bounds, no beginning, no end. Music perhaps after today, you'll no longer consider our universe synonymous with infinity. After all, what has a beginning, sooner or later, will find its end. The infinite nature of the universe suggests that it must be infinite not only in terms of space, but also in terms of time, which means it would contain an infinite number of stars. If that were the case, our sky would be densely populated with stars and incredibly bright at all times of the day. However, the darkness of the night sky suggests that the timeline of the existing cosmos is not infinite. So, according to this theory, the universe was created as a result of a powerful explosion from a point of densely packed matter and energy, also known as singularity. Mark a sheet of paper with a small dot, then try to crush the paper to the size of that dot. Now imagine, before this Big Bang, our universe was contained in a space smaller than the dot you just drew. The amount of pressure within it was incredibly high, and it feels natural that eventually, this presence would result in expansion. Just as the paper in your hands is trying to take its previous form, the universe expanded, albeit on an entirely different scale. And everything in the universe, past, present, and future, is the consequence of that event. Everything we see and feel, the matter that we're composed of, everything formed thanks to that process. So, how was everything we see around us born from such a destructive process? At the beginning, a millionth of a second almost instantly spread the extremely high temperature substance, the plasma. From that emerged the elements that make up our world today, such as protons, neutrons, electrons. This process is known as baryogenesis or baryon synthesis. It led to conditions that made it possible for hydrogen and helium to form, which subsequently formed the stars. The life cycle of a star will form everything that our world is made of. First, let's talk about how we were able to have a glance all the way back to the start of the universe. Then we can discuss why it is so difficult to find its edge. To travel to the past, you'll only need a TV. And now that it's in front of you, watch without a signal. All we see on the screen are interference and white noise. But right now, you're watching a process that's a direct consequence of the Big Bang. Look closer. This is relic radiation of the universe, also known as cosmic microwave background or CMB. In the 70s, the process of space exploration resulted in the discovery of a number of zones we could not see properly. Some of the images looked as if there was a lens flare. The strange thing was that all the cosmic sources of light known at the time, such as the dying or emerging stars, were too far from these flares. They couldn't have been the reason for this phenomenon. This is how the scientists learned about relic radiation, and what you're seeing on the screen is the effect of this radiation. This white noise is the real echo and voice of the early universe. When scientists set out to research this phenomenon, it became apparent that the radiation occurred at the very moment when the universe was first lit up by the emergence of chemical elements. We learned that this radiation is not related to the stars or other sources of light. Thanks to the Oumuamua probe, we were able to receive the first comprehensive map of relic radiation in the universe. More detail was added to the map thanks to the work of the Planck Space Observatory. Take a look at it. Doesn't it look like the previous TV image but in color? This echo of the Big Bang is dispersed across the universe incredibly even. This is the light of the birth of our universe that has existed since the Big Bang. And thanks to this light, we're now able to see the true structure of the universe and realize the universe is finite. The things we are able to see or calculate using a computer model were called the observable universe. And the things that we can explore within it are known as the meta-galaxy. So where are we within this system? Let's have a look. There's our home planet Earth and the solar system. The solar system is part of the local stellar system along with the neighboring stars and their systems. We are part of the Milky Way galaxy. The galaxy itself is part of a larger group of galaxies. As we zoom out even further, we can see our place among other galaxies in the Laniakea supercluster. Seems huge, doesn't it? The final reference for scale will be the observable universe. In the grand scheme of things, we are only a tiny grain of sand. But even an entity of this size has its limits. We're facing the fundamental question: is everything that we see the extent of the universe? How can we see beyond the light emitted by stars? Take a closer look at the map of the cosmic microwave background. The brighter spot signal changes in temperature in space, signifying where star systems, galaxies, and supergalaxies can be found outside of our visual range. Is it possible to use relic radiation to see the entire universe? Think about the night sky. If you're on a brightly lit street, or next to another source of light, such as a campfire, it's difficult to make out the faraway stars in the sky. The same principle applies here. Relic radiation illuminates the universe and all its glory. However, its light also hides the dark alleys of the universe. For example, the areas devoid of stars, and it also hides black holes and places in our universe that have not yet been reached by light. Remember, the consequences of the Big Bang are still relevant. So, is there anything beyond this edge? It seems that the answer to this question was found through the inflation theory. According to this theory, the bounds of our universe continue to expand at a rapid exponential pace, leading to a conclusion that the universe cannot have a concrete boundary. Let's circle back to that piece of paper you crumpled at the start. Has it begun to unravel yet? It's obvious that sooner or later, it will come back to being the same size as the sheet you grabbed initially. The most elementary physics dictates that the inflation theory has its issues, because the laws of physics work in the same manner in every part of our universe. Even though scientists found countless things that confirmed the rapid expansion of the universe after the Big Bang, as well as plenty of facts that suggest continuing expansion, that's far from being the big picture. For example, observation showed that galaxies and stars have an ever-increasing speed as they move apart from each other. Seemingly, this would confirm the inflation theory of the universe. Nevertheless, questions remain. What was happening when the universe did not yet exist? If the universe emerged from singularity, does that mean that there was a time before this singularity existed? If the same laws of physics apply in different parts of the universe, then why is the universe so large? Where did the energy necessary to create it come from? Doubts were always present, and the more scientists learned about the structure and history of our world, the more questions remained unanswered. The Big Bang theory, and subsequently the inflation theory, were not able to answer these questions. Fortunately, there was a different theory that was recently proposed, which may be able to explain to us the things we see in the universe now, as well as things that happened before, and things that will likely happen in the future. Theory of the cyclic universe, also known as the oscillating model of the universe. The foundation for this view of the universe as if it were a living organism with its own cycles of existence was laid at the beginning of the 20th century. The Friedman-Robertson-Walker model suggested that, since the universe has been expanding since the Big Bang, it is only logical that at some point, it compresses back into a singularity. According to this theory, the universe, as we know it, exists between periods of expansion and contraction. However, soon their theory was revealed to have a serious contradiction, because the concept of entropy had been discovered in the 1930s. Which is the process of endless dissipation of energy through space and its decay. Entropy would mean that each cycle of the universe would require more and more energy. Friedman and his colleagues could not give an answer as to where this energy comes from. Initially, think about your piece of paper. After all, without the force from your hands, nothing could have happened to it. For almost 80 years, this model was set aside as a false theory. But at the beginning of the 21st century, it was brought back from the dusty shelf. Two Princeton scientists, Paul Steinhard and Neil Turk, have come up with a completely new version of it. Their model is primarily based on string theory. It is rooted in the idea that everything material in the universe consists of tiny particles, which collectively make up something roughly similar to strings. For example, the smallest particle of light is called a photon, and it manifests as rays of light made up of many of these particles moving in a certain direction. We see this movement as light. The same principle applies to sound, gravity, heat, and so on. According to their theory, there is no beginning or end of the universe. There's just endless strings of matter that interact with each other. According to their scenario, the history of the universe is an endless cycle. But in this case, instead of starting a new universe, it denotes the next phase of its existence. According to their model, our universe emerged as a result of a collision of two three-dimensional worlds. So why can't we see this neighboring world? According to string theory, in addition to the three-dimensional world visible to us, matter exists in several additional dimensions. And so it's not unreasonable to theorize that two three-dimensional worlds could collide within the framework of an additional hidden dimension. String theory suggests there could be up to 50 dimensions in which matter exists. As these three-dimensional worlds collide, they stick together, and the kinetic energy from the impact is converted into quarks, electrons, photons, and other simple elements of matter. In turn, this process generates the energy for the expansion of our universe. So, two colliding worlds give each other energy. This event gives rise to life in one of them. But in the end, our universe has a certain limit of both expansion and life as we know it. Over time, it will return to its normal state. After all, the energy that fuels expansion will come to an end. And then the reverse process will begin, compression. This suggests that our universe really has an edge. It's just that the edge is not geographical and doesn't look like a tangible boundary. Instead, it marks the end of the cycle and the beginning of something new. The boundary begins where our universe collides with other universes in its motion, interacting and receiving the necessary impulses for its development. Cycle outside the three-dimensional world we are accustomed to. Who knows? What are the laws of physics beyond our universe? In the meantime, the theory of the cyclic universe is waiting for its practical confirmation. The main problem for scientists now is finding evidence of the existence of extra dimensions. So far, their existence is confirmed only by theoretical calculations. The sheet of paper you crumbled earlier is a great example, because to that sheet, you are the inevitable force that changed its structure. You are the catalyst for the change, and you are the one controlling when to stop the compression process. Humanity is yet to determine what acted as the catalyst for the change of the universe and what it will lead to in the future. Whether it was an impact from a neighboring universe, the Big Bang, or something else entirely, we're very close to finding that answer. To be able to look over the edge and say, everything happened for a reason. Does Planet 9 really exist? Since Pluto lost its planet status, scientists have not abandoned their attempts to detect other large objects on the edge of the solar system. After all, there is something beyond the orbit of Neptune that significantly affects the trajectory and revolution of celestial objects like asteroids and dwarf planets. And this isn't the kind of something we can detect with telescopes. Recent research suggests it could be a miniature black hole or even a cluster of dark matter. In this video, we'll examine the mysterious ninth planet, its properties, size, and whether it is a planet at all. Concerns became especially prevalent when scientists closely studied the movements of trans-Neptunian objects in the Kuiper belt. an area on the edge of the solar system similar to an asteroid belt. Astrophysicists Konstantin Batygin and Michael Brown studied 6 distant objects in the Kuiper belt, including dwarf planets and planetoids such as the dwarf planet Sedna. They found that the objects followed elliptical orbits, pointed in the same direction, but moving at different speeds. This was a rather unexpected discovery, and Brown even made this analogy. This kind of result is as if there were a clock with 6 hands moving at different speeds. But as soon as you look up, all the hands are in the same spot. Brown implied that this type of event is very unlikely. On top of that, the orbits of these 6 objects are tilted at the same angle, about 30 degrees downward, in the same direction, relative to the plane of the 8 known planets. The chance of this happening is about 0.007%. The first proposed theory was the presence of certain objects near the borders of the Kuiper belt that would affect gravity. Therefore, if that were the case, the mass of the belt should have been 100 times greater than it is today. Computer simulations using a small planet have shown that its mass would be insufficient to align objects in this manner. However, if you run a similar simulation with a massive planet the scale of Uranus or Neptune, the mathematical model converges and practically duplicates the real-world calculation results. The work of Batygin and Brown sets limits on the possible mass of the 9th planet, the location of its orbit, and its position in the sky. According to calculations, the mass of the planet is 5 to 20 times greater than the mass of Earth, and its diameter is 2 to 4 times larger than our planet's. To see this planet directly through a telescope is almost impossible. It is too far to register in our visible spectrum, so we have to search for it using its faint infrared glow. However, with the mass of only 5 Earth masses, it wouldn't give off much heat. Additionally, such a distant planet would revolve around the Sun very slowly, so it would be impossible to detect its movement with observation alone. It's only possible by comparing images taken at different times, and this may take dozens of years. Unfortunately for astrophysicists, it's most likely that right now the planet is the furthest removed from the Sun in the northern hemisphere of the sky, with the radius of its elongated orbit on average in the range from 380 to 980 astronomical units. Even all of the data collected so far does not provide a complete picture of the potential location of the mysterious planet. The search area is approximately 600 to 800 square degrees in the night sky. For reference, the full moon only occupies 0.2 square degrees in the sky. In an attempt to narrow down the planet's orbit, the researchers compared simulation results with real Kuiper belt objects. A 4-billion-year-old model of the solar system was built. Scientists wanted to understand how the gravitational pull of the largest planets and the 9th planet could affect the orbits of thousands of objects in the Kuiper belt. Although Batygin and Brown actually proved the existence of a certain object that influences the position of other celestial bodies, recent research conducted over the years 2020 to 2022 has cast doubt on the existence of a massive planet. In a relatively recent study from 2021, critics of the Batygin-Brown theory have discovered about 300 new objects in the region of the Kuiper belt where Batygin and Brown theorized the presence of the 9th planet. Astronomers scanned the better part of the sky with the 20-foot Atacama Space Telescope in Chile in search of the new planet, and spent 6 years studying 87% of the sky accessible from the southern hemisphere. Reportedly, a detailed examination of the orbits of objects in question revealed that every case of orbit synchronization can be explained by known physics effects, except for 2 celestial bodies. But even these 2 anomalies are an exception out of 300 objects, and in a way, they confirmed the new theory. Why do discoveries in these orbits not coincide with Batygin and Brown's predictions? The answer may be that the 9th planet theory is simply incorrect. However, the nature of the strange behavior of the orbits of some objects in the farthest reaches of our solar system hypothesized by some astronomers to be shaped by an unknown ninth planet, can instead be explained by the combined gravitational force of small objects orbiting the Sun beyond Neptune. The alternative explanation, Planet 9 hypothesis put forward by researchers, proposes a disk made up of small icy bodies with the combined mass as much as 10 times that of Earth. When combined with the simplified model of the solar system, the gravitational forces of the hypothesized disk can account for the unusual orbit architecture exhibited by some objects at the outer reaches of the solar system. The researchers created a computer model of the detached nose, as well as the planets of the solar system and their gravity, and a huge disk of debris past Neptune's orbit. Astrophysicist and Tranix allows, if you remove Planet 9 from the model, and instead allow for lots of small objects scattered across a wide area, collective attractions between those objects could just as easily account for the eccentric orbits we see in some nose. Earlier attempts to estimate the total mass of objects beyond Neptune have only added up to around a tenth the mass of Earth. However, in order for the nose to have the observed orbits and for there to be no Planet 9, the model requires the combined mass of the Kuiper belt to be between a few to 10 times the mass of the Earth. Another team of scientists used the infrared astronomical satellite IRAS and the Akari infrared telescope to search for the ninth planet. 2 surveys were performed and photographed over 20 years apart, giving any hypothetical planet enough time to move to a slightly different part of the sky. The scientists assumed that any distant planets would be quite close to the equatorial plane of the sky, and then studied the data marking potential planets. They have found over 500 candidates. Judging by the energy distribution of their spectra, most of them have orbital distances of less than 1,000 astronomical units. This means that most of these objects were either inside or near a faint nebula. A nebula is a cloud of interstellar gas that's difficult to see with the naked eye because it emits infrared light, or simply put, heat. Turns out that all the discovered candidates are not planets at all, but rather echoes of a faint nebula. A large planet, clusters of small objects, or a glimpse of a distant galaxy. These are perhaps the simplest explanations for the unusual behavior of trans-Neptunian objects. Scientists ask themselves a logical question: what kind of object would have enough mass to change the orbits of other celestial bodies, yet not be visible to us? This prompted theorists to consider a radical hypothesis. What if the ninth planet is a small black hole that can be detected by theoretical radiation emitted around its edges, the so-called Hawking radiation? There is a contradiction that relates to the mass of such an object, since it is believed that only the most gigantic stars are large enough to form a black hole. The black holes they would leave behind would have a minimum mass of around 5 times greater than the Sun's mass. But what if the extreme conditions of the early universe made it possible for smaller black holes to form? A group of astronomers from Harvard University plan to start their search for such objects as early as 2023, as part of the Legacy Survey of Space and Time LEST project, to help them find black holes in far corners of the solar system. Astrophysicist Avi Loeb developed a method to search for flares that occur when a black hole collides with small objects in the Kuiper belt and the Oort cloud, a region that could potentially contain several trillion bodies surrounding our system. The researchers say that sometimes the objects within the Oort cloud, such as comets, can interact with lurking black holes, creating a visible flash of light possible for Rubin's observatory to detect. Thus, if scientists could confirm that a small black hole the size of a grapefruit with the mass of 5 to 10 times the mass of Earth orbits the Sun, this could provide an answer to one of the greatest mysteries of modern cosmology, the formation of black holes. However, there is another theory, exotic, and yet just as deserving as others. What if, out there at the edge of the solar system, there's an object made of dark matter? We see evidence of dark matter all around us that revolve too fast around the centers of their galaxies. galaxies that move too fast within their clusters. A new hypothesis now suggests that most of the dark matter can concentrate into objects the size of Neptune, the so-called dark matter planets. Although these planets remain invisible to us, they can create an atmosphere of helium and hydrogen. And this can lead to the fact that reaching critical temperatures would trigger nuclear fusion inside the planets, which would help us discover them. Dark matter forming into planets may explain why no object with a mass approximately equal to the mass of Neptune has been discovered. In the aforementioned research, scientists believe that if dark matter planets exist, they clearly formed when the universe was very young and remained static for billions of years. In the early universe, the temperature was too high, which prevented the formation of larger objects. However, dark matter does not interact with ordinary matter nor light, and could, therefore, freely assemble into such planets. According to this theory, instead of being evenly distributed throughout the galaxy, most of the dark matter will be inside these relatively compact spheres with masses ranging from the mass of an asteroid to the mass of Neptune. These hypothetical dark matter planets may have first accumulated a layer of helium, since it was the first chemical element to break away from the plasma state of the early universe and later attracted hydrogen gas, creating a dense atmosphere around the helium, similar to the layers of gas around giant planets. What would we see inside a planet like that? That's hard to say. Submerging into such a planet would be very strange. A bright layer of hydrogen would be warm, since it's gravitationally bound to a dense object. Friction would cause it to glow. After the layer of hydrogen, we would reach the helium underneath. And as soon as we pass through the helium, we would see nothing, absolute emptiness. The core of the dark matter planet would be completely invisible. You'll find yourself surrounded by a membrane of luminous hydrogen-helium plasma. The flash from the ejection of matter could compete with a supernova in its brightness. In conclusion, let's address the expediency of the search for the mysterious ninth planet. Although searches have so far not revealed a single planet at the edge of the solar system, this does not mean that the search was completely in vain. The ninth planet theory has sparked an unprecedented surge in research into the Kuiper belt and other trans-Neptunian objects. The search for Planet 9 may eventually lead to something even more significant for scientific progress. For example, Batagan claims that the discovery of the ninth planet, which seems so strange to us, would actually make our solar system. What origin of life? Good. By now, we have all become accustomed to the idea that life originated in the ocean. But certain questions still make scientists have fierce arguments with each other. For example, how did life transition from water to dry land? Why would a mass meteorite strike be useful? Is collision with another planet important for the development of life? What did Earth look like throughout the first millions of years of its existence? And what obstacles did it have to face? Some of these questions already have answers, and we will share them with you right now. Life that originated in the water and later made its way to dry land appears as a very plausible theory. After all, the oceans currently cover more than 70% of the Earth and contain many different organisms. Some of them studied so little that scientists still continue to discover new species. Once on land, these lifeforms successfully adapted and evolved to eventually become human. Everyone remembers Darwin's theory where a fish suddenly decided to spend its vacation on dry land. Modern scientists explain this theory. Fun fact, no matter how many repetitions of Darwin's theory you read, scientists take this theory as a starting point, just as often. The main question is, what is required for life to form, except for the ocean? To answer this question, we must travel to the distant past of the solar system. The process of creation of the solar system is similar to our neighboring star systems. At some point, about 13.6 billion years ago, the Big Bang happened. According to scientists, it was responsible for creating the universe as we see it in telescopes. And the consequences of this event led to the first chemical elements forming hydrogen. which compressed and heated under the pressure of the energy from the explosion and turned into a new element, helium. We refer to this bunch of compressed hydrogen, which turns into helium, as a protostar. But the protostars did not stay with us for long. The main benefit of their existence is the emergence of new chemical elements, which became the building blocks for the origin of life. First and foremost, it led to the emergence of ordinary stars. Every star has a life cycle throughout which the star is akin to a factory. Something is burning, there is some smoke, and streams of resources are flowing through to produce something. Simultaneously, all of these processes affect the ecology and environment. So our sun, like any other star, does the same thing, but on a cosmic scale. Then the life of a star factory is pretty prosaic. It either expands to a supernova or transforms into a red giant or a dark dwarf, followed by attenuation and death. Alternatively, a star can turn into a black hole. We know for sure that the sun will become a red giant, eventually, expanding to encompass nearby planets, including us. However, we still have 5.5 billion years before that happens, so we'll have enough time to finish watching our favorite TV shows. What is so special about our solar system? Scientists theorize that the sun was created by a supernova being destroyed not far from the future solar system. Thus, our star, having arisen from compressed clouds of gases, will have eventually absorbed such a high amount of matter due to gravity, that it will be enough not only for its existence, but also for the creation of the entire solar system. Everything that was not a part of the new star began to revolve around it, flattening and acquiring the shape of a disk. That's a huge amount of matter. Some of it will be lucky to become a planet, and some will leave the sun's immediate orbit to become a comet or a dwarf planet. The future cradle of humankind came into existence somewhere around here. At the start of its life, Earth was something like a stew of lava rocks, in a liquid form and crazy mixtures of gases released during the melting process. Near our surface, the temperature exceeded 1,200 degrees. There was no air, only carbon dioxide, nitrogen, and steam. Moreover, the planet was being continuously bombarded by comets and meteorites, some attracted by the planet itself, and some attracted by the sun. This is where the water particles that eventually land on Earth come from. But at this point, there is no talk of any life. Earth receives the most powerful blow in its history, but also the most useful, as it turned out later. A planet the size of Mars, which was later named Theia by the scientist, crashes into us. The result of this collision is the formation of the current shape and size of Earth. But even more importantly, the fragments form into our satellite, the Moon. Initially, it was much closer to us, 13.6 thousand miles. This will have an effect later on. The importance of the Moon will become more evident. As Earth cools down over time, Earth's temperature began to lower, which led to Earth's crust forming a thick layer of everything that our planet collected due to gravity as it was forming. And after the cooling process, only the very core of the planet, molten iron, remained hot and liquid. It is the activity within the core that creates the magnetic field around Earth, and keeps it at its stable moving pace, both around its own axis and around the sun. As the temperature kept dropping, the planet experienced its first rainfall around 3.8 billion years ago. It was subjected to a meteor shower, the remnants from the formation of the solar system bombarding Earth. But inside these bombs, there was also something useful, namely, water. Those are not yet the kind of rains we're used to. At the time, the speed of Earth's rotation was so high that a day only lasted 6 hours. However, thanks to that very useful rain, the first ocean formed on Earth. Meteor showers lasted 20 million years, so the low water content in each individual meteorite was not a problem. Quantity led to quality. At this stage in Earth's development, scientists had a question: where did water actually come from? There are two theories regarding this. Some believe that all the water was brought to us by meteorites. The second theory suggests that there was already water on Earth. The argument was solved by time and new discoveries. Both theories turned out to be right and wrong at the same time. Studying the soil from the moon's surface revealed that the then young and active sun burned everything that could evaporate from the planets, including water and gases. So, the scientists still cannot definitively say whether there is more water of meteoric or terrestrial origin present on Earth. And most likely, they will never be able to answer that question. But the main thing is that the collision of Earth and Theia became a catalyst for the beginning of the cooling process of the planets, and subsequently the formation of Earth's atmosphere, which would serve to protect it from the sun. The existence of the atmosphere became the shield that maintains everything needed to create life, and doesn't let anything harmful in. How did the atmosphere form? Active due to this volcanic activity, water evaporates, turning into clouds, which then turn into rain. For millions of years, rains fall to Earth's surface, pulling into lakes and seas and oceans. And this worldwide ocean was very stormy. You know how the moon influenced the tide. At the time, the moon was much closer, and its rotation around Earth caused such powerful ocean storms, we could hardly imagine the scale. Some waves reached no less than 1,000 feet in height. Meanwhile, the winds on Earth were nearly as fast as the speed of sound. And so, the ocean is raging. The storm is at full swing. Where ice life? Contemporaries generally agree on one thing. Back then, Earth's oceans were an ideal place for the emergence of life. But there are several problems. The main question is, how did organic matter, that is, chemical elements, that are the building blocks of life, come to exist under these conditions? Let's break it down. Water and Earth's atmosphere at the time, specifically nitrogen, hydrogen, and carbon dioxide, are elements from the inanimate part of the chemical elements, the so-called inorganic chemical elements. To answer this, let's look at the theory that was developed by Oumuamua, an academic from the USSR, in 1924. As well as a similar theory put forward by a biochemist from the UK named Haldane in 1938. In essence, these theories are simple. The ocean of that time was constantly replenished with organic substances from the atmosphere, which was constantly struck by lightning, thanks to the endless storm of that period. It was under the influence of these electrical charges that these elements in the atmosphere turned from inanimate, inorganic into living, organic, and fell into the water. Once they were in the water, the particles slowly gathered together and formed a broth of organic matter, which would subsequently develop into living organisms. The way these particles behave was similar to the behavior of cells. They can grow, divide, and absorb other chemical elements. But the truth is, the organic matter only acts as the building blocks of the body. Creating life itself requires a team of workers and a foreman to bring everything together. The foreman of our cells is our DNA, an entire library of how everything works, from reproduction to building complex structures from sets of cells. The workers performing the task are RNA. The Oumuamua and Haldane theory is similar to the story about Frankenstein's monster, whose inanimate matter was also brought to life by a lightning strike. The main thing that we know is that life arose somewhere in the ocean, and for 300 million years existed in the form of single-celled organisms. They were not particularly in a hurry to turn into people, were they? But to be frank, the conditions of the ancient Earth would not have given something more complex a chance to develop. The single-celled organisms that existed then were prokaryotes. The main difference between them and us is that their organism consisted of one cell, without a protective membrane and, in most cases, without a nucleus. A good example of the currently existing prokaryotes is bacteria. On Earth, first oxygen came to exist in sufficient quantities to begin to form the atmosphere in which we now live. And then, within 1 billion years, Somewhere between 3.5 and 2.5 billion years ago, a new miracle took place. Single-celled organisms, even in such a literally toxic atmosphere, have learned to use the energy of light to convert water, carbon dioxide, and solar energy into their first food, glucose. The byproduct of the process produced even more oxygen. We refer to this miracle as photosynthesis. After the cooling of the Earth and the formation of the ocean, a terrible thing happened. Two ice ages took place. The first, known as the Pangala glaciation, lasted 500 million years. The second, the Huronian Ice Age, was slightly shorter but almost exterminated life on Earth. The Huron glaciation lasted 300 million years. It was caused by an oxygen catastrophe. It happened due to the fact that, thanks to photosynthesis, unicellular organisms began to release so much oxygen that it led to the extinction of all unicellular organisms that existed without oxygen. And so, aerobic organisms, the organisms that need oxygen to exist, became dominant life forms on the planet. Next, prokaryotes continue to evolve into eukaryotes. Both are closest and the most ancient ancestors in terms of cell structure. Eukaryotes were able to compete, absorb, and destroy their own kind. They used solar energy as the main source of life, and were also able to reproduce. Eukaryotes gradually moved closer to dry land, formed by volcanic activity, producing more and more oxygen along the way. In the shallow water, they united to form the prototype of underwater trees, stromatolites. First, they became red algae, with their key feature being the ability to reproduce sexually. This skill will give an impetus to evolution, resulting in the next prototype of modern nature, mushrooms that grow on land. 540 million years ago, the Cambrian explosion occurred, characterized by the dramatic increase in the number of living organisms. This event prompted the emergence of future animals, plankton, and calcium microbes. 70 to 80 million years later, another rapid leap in evolution takes place when most of the species known to us today come to existence. The first animals to set foot on dry land were arthropods. At first, they simply roamed the land in search of more saturating food than algae and plankton, but then, they never went back into the water. According to scientists, one of the most interesting species that transitioned from life in water to life on land is the tiktaalik fish. Its limbs were like paws, which made it possible for them to move out of the water. For 360 million years, plants, having learned to reproduce by seeds, spread across the land, and more, the insects will soon fly into the air.